So you're looking for xy, you put xg here, yg here. You're looking for iyz, you put yg here and zg here. And then you carry out the integral. So iyz becomes what? Becomes the whole thing integrated, and the dm, you already have this one here. You just put this one again. So in this integral, you also have rho and h, take it out, because they are constants. And for yg is y. What about the zg? Zg is h over 2. Take it out because it's constant. So that makes this to be h squared over 2. And then you integrate the rest. So here you have yg, which is y times the whole thing here. So this becomes y times a minus y dy. And it's also from 0 to a. And this becomes what? This will give you the result of total mass over 6 times a times h. Like this. Well, I think I missed an h here. There should be a, no, there's no h because it's a squared. In the mass, total mass, you already have an h. So that's correct. So this is iyz. Now, what about izx? What about izx? What do you think? What about izx? Can we use the property of symmetry to find it? Izx is also iyz. And how do we figure that? It's because you notice that x-axis and y-axis are what? They are basically identical, right? You can swap them. You can swap these two. So here, all you need is to notice that as long as you have a z-axis here, if x and y are identical, and then in this case, they are. So this izx is just the same. Now for this, we have found all 6 values for mass moments of inertia and mass products of inertia. So that's what we have found so far. Now let me get back to this point to show you that why the mass products of inertia on the symmetric plane is 0. Why is that? So first of all, let's look at the xy plane. On the xy plane, we have x here, y here, 0, and of course, it's a here and a here, right? Correct? It's like this. Now, where's the center of gravity? Center of gravity is right here. 1/3 g, and this is the y prime, and this being the x prime. So x prime and y prime are the axes passing the center of gravity. Now, the concept of what we call parallel plane theory is this. You're not looking at just individual axes, you're looking at the whole plane. So if the whole plane has a symmetric axis, and then this term will always be 0. Will always be 0. So in this case, what do you mean by axis of symmetry? Well, very simple. You can just try to find, can you identify an axis like this? And on both sides of this axis, the object, a 3-dimensional object, appears to be identical. If you can do it, and then this value will be 0. So in this case, yes, there exists an axis of symmetry. If this exists, and then this will be 0. Okay? So that's why we have all these terms to be 0. Now, in the end, let's put everything together. Step 7. And I need to show you this result before we can continue this problem on Monday. So step 7. Now you have all this together. So we can put everything together like this. You can put in like a matrix. And here on the diagonal term is going to be IXX, IYY, and IZZ. Remember, they are mass moment of inertia. Off diagonal terms are what we call products of inertia. And be careful that they are negative by definition. So you're going to have negative IXY here, negative IYXZ here, and negative IYZ. And this whole thing must be symmetric. This is what we call inertial tensor. And what is a tensor? Tensor is a term that we use in abstract mathematics. We call a quantity with multidimensional values, and those kind of quantity we call it tensor. So if you remember, maybe from high school algebra, or maybe from calculus, scalars are what we call zeroth order tensor. Vectors, what we call first order tensor. Of course, what are scalars? Like amplitudes, 1, 2, 3, 4. They are scalars, and they mathematically we call zeroth order tensor. What are vectors? Like the velocity vector, acceleration vector, displacement vector, they are what we call first order tensor. And the next one is what? Matrices. What are matrices? They are second order tensor. Now you see why mathematicians like to use tensor, because this way they don't have to bother themselves with the scalars, the vectors, or matrices. They are just names for engineers to use. Of course, in this three-dimensional reality, we will probably embrace only three-dimensional objects. For higher order quantities, it's difficult for us to picture, right? So every object in the three-dimensional world must obey this what we call dimensional limitation. So whatever exists in this dimension must be equal to this dimension or less, cannot be more, which is why I cannot show you the fourth dimension object here, because we are in the three-dimensional world. However, mathematically, you see, for tensors, the order can go as high as they want. Correct? You can define the sixth order, fifth order, even the 100th order. Only we cannot visualize them in this three-dimensional reality. Okay, so tensor is just a name to code. It's just to connect whatever we learned in engineering with mathematics. So next time, I'm going to show you how we can use this, because we found that these are the axes. Now we have all these terms not being zero, but turns out that if you rotate your xy to certain angles, you can actually eliminate off-diagonal terms. And that is what we're going to do on Monday. And that's what I call determination of principal axis of inertia.